At this point, we're going to discuss the third and final portion of the basic instruction set, the program control instructions. The program control group of instructions may be further divided into smaller functional groups. We'll begin by discussing the branch instructions because they comprise the largest and most important group of program control instructions. A branch instruction orders the CPU to test some condition and then take some action based on the test results. For example, a branch instruction may direct the CPU to repeat a portion of some job until a predefined condition is satisfied. When the condition is met, the central processor exits from its program loop and proceeds to the next instruction in the sequence. The conditions that are tested by the CPU are the 4 condition code bits that we discussed earlier in this unit. In other words, when the CPU decodes a conditional branch instruction, the opcode tells the central processor which condition code bits are to be tested. There are 16 conditional branch instructions. They're called conditional because a branch only occurs when a specific condition is met. For example, the instruction may ask, is the Z bit set? If this condition is met, then the program branches to some new specified location. If it is not met, then the program simply continues with the next instruction. Here is the format of a branch instruction. The word is divided into 2 parts. The first part indicates what condition to test. The second part determines where to go or branch once the condition has been satisfied. Let's look at the first portion, or high byte, of the branch instruction. The entire high byte, bits 8 through 15, contains the opcode, which specifies the test condition. The second part of the word, or low byte, is known as the offset. The offset is a value used to determine where the CPU is to branch for its next instruction if the condition is met. In other words, how far is the new location offset relative to the updated PC? To summarize, we test the condition specified by the high byte, and if it is met, we go to the location specified by the low byte. A typical branch instruction looks like this. The high byte indicates the condition branch if not equal to 0, or BNE. The low byte specifies the location that the program will branch to when this condition is met. The BNE instruction tests the condition of the Z, or 0 bit, in the PSW. If the Z bit is clear, indicating not equal to 0, then a branch occurs. If the Z bit is set, indicating a 0 condition, then the program does not branch, but simply continues with the next instruction in the program. Let's take a look at how branch instructions are used in typical PDP-11 programs. Suppose we were searching for the value y located somewhere in a large table of values representing constants used in mathematical computations. It has come to our attention that the value y is erroneous and must be incremented. However, our first job is to find it as quickly as possible in the table. How do we go about this? This flow diagram represents a small program that will search for y and then increment y when it has been found. First, we get an entry from the table of values. Then we compare it with the value we're seeking, in this case, the value y. We next ask if the Z bit is clear. If the answer is yes, we know that we have not found the value we're seeking, so we get the next entry and compare it with the value y. However, if the Z bit is not clear, that is, if it is set, it indicates the results of our comparison were equal. Therefore, we have found the desired value, so we go to the next instruction, increment y, which is the job we planned to do in the first place. The first step in implementing this program is to set up a pointer. Because we want to point to the first entry in the table of values, we use the move address R0 instruction to move the first address of 600 into R0, which then becomes our pointer. Next, we want to compare the entry with the known value y. After the comparison, we must move our pointer to the next entry in the table. We do this by using a compare byte number y R0 plus instruction. This instruction compares the value y with the contents of the location specified by the pointer, in this case the first entry. Because we are using the auto-increment addressing mode, this instruction then increments the pointer after the comparison has been made. In this case, the results of the compare are not equal. Therefore, the Z bit is clear. Testing this condition is accomplished by the BNE start instruction, which looks for a not equal condition. It asks, is the Z bit clear? Since we know that a cleared Z bit means we have not found the desired value, we branch back to start and repeat the entire process for the next entry. In other words, we form a loop. Let's see what happens once we find Y. When Y is found, the comparison between the Y in the table and the Y we placed in the instruction results in a match or an equal condition which sets the Z bit. How does this setting the Z bit affect our branch instruction? The BNE start instruction looks for a not equal or Z bit clear condition. However, we know now that an equal condition exists and the Z bit is set. Therefore, the program does not branch, but goes to the next sequential instruction, which is increment Y. Notice that the BNE start instruction causes a branch back to the location labeled start. This branch location is determined by the offset value contained in our BNE instruction. Offset is just another word for displacement. This displacement refers to the distance between the point we wish to branch to and the current address in the program counter. It is extremely important to notice that the offset is calculated relative to the updated PC. In this case, the branch instruction is at location 610. We want to go back to an address of 604. Notice two important points. First, the compare instruction fills two word locations because it uses the immediate addressing mode. Secondly, the offset is calculated between the updated PC and the desired address. In other words, the address is 3 words back from the PC, or we could say the offset is -3. The offset can be used in either direction. Here, our offset is 2 words forward or +2. Again, notice that the offset is relative to the PC. It is the distance in words between the PC and the desired address. Caution must be exercised when calculating any offset value. Here, our branch instruction is at location 602. We want to go to location 614. Because the offset is relative to the PC, it is +4, 4 words forward from the PC. If you should get careless, you might forget about the PC and calculate the distance between the BNE instruction and the desired address. Because this distance is 5 words forward, it seems to indicate an offset of +5. However, this value is wrong. Remember, the offset is always calculated relative to the updated PC. As we've said before, the offset is relative because it represents a displacement from the PC, which may be located at any point in the program. The offset may be positive, indicating the branch point is forward from the PC, or it may be negative, indicating that the branch point is backward from the PC. The offset range is limited. We cannot branch to any point in the entire program. We can, however, go forward anywhere from 0 to 177 octal word locations, or we can go backwards from 1 to 200 octal word locations. We'll discuss this range more fully a little later. This is a low byte of a branch instruction. The highest bit, bit 7, is the sign bit, indicating whether the offset is negative or positive. When the sign bit is a 1, the offset is negative. When the sign bit is 0, then the offset is positive. The remaining bits represent the offset value. To summarize, the sign bit indicates direction. The remaining bits indicate distance. For example, here we have the low byte of a branch instruction. Notice that the highest offset value that can be loaded into the magnitude portion is all 1s, or octal 177. These are examples of positive offset values. The sign bit contains a 0, indicating positive. In the example at the top, the magnitude portion contains all 0s, representing the lowest possible positive offset. The magnitude portion can be increased continually until the maximum limit of all 1s is reached. Thus, positive offsets may be anywhere within the range of 0 and octal 177. Using negative offset values is slightly more difficult. Here, a 1 in the sign bit indicates a negative offset. The magnitude portion contains all ones, or octal 177. The entire low byte, including sign, represents an octal value of 377. The number 377 is the 2's complement form of -1. In other words, we have a negative offset of 1. Here's another example of negative offset. -170 is read as 370, which is the 2's complement form of -8. This is a summation of negative offset values. We start out with 377. This is an equivalent to all ones and calls for an offset of -1. 376 is the 2's complement equivalent for an offset of -2, and so on. 202 is the 2's complement of -176, down to the last value of 200. This is represented by a 1 followed by all zeros and is the 2's complement representing the maximum negative offset of 200. When you, as a programmer, are dealing with positive offsets, it is very straightforward. You simply write the desired positive offset value, keeping in mind it must remain within the range of 0 to 177. The PDP-11 computer reads the offset in the same way. In other words, the programmer and the computer are speaking the same language. However, negative offsets require a translation process because the programmer and the PDP-11 computer speak different languages when dealing with negative numbers. The programmer may want to use an offset of -5. Unfortunately, the computer can only understand the 2's complement form, which in this case happens to be 373. Fortunately, the assembler handles this translation problem for you. If you want to go back 5 locations, for example, then simply type in a -5 after the branch mnemonic. Thus, BNE -5 is the assembler syntax for branching back 5 locations if the result is not equal to 0. In summary, a positive offset indicates the distance forward from the program counter. This distance can be anywhere from 0 all the way up to 177 octal words. On the other hand, a negative offset represents the distance backwards from the program counter. This distance may be anywhere within the range of 1 to 200 octal words. Remember, when using negative offset, the value loaded into the low byte of the branch instruction is always in the 2's complement form. There are 2 offset values that must be used with extreme caution, if used at all. An offset of -1 is a dangerous offset value. Remember that the offset is relative to the PC. Therefore, an offset of -1 causes a branch back to the very instruction causing the branch. In other words, we become locked in a continual loop from which there's no escape. A 0 offset indicates there's no branch at all. The program simply continues with the next instruction. Although this offset could be used if desired, it would serve no useful purpose. Why use a branch to the next instruction when the program always goes to the next instruction anyway? Now we're going to show you how the assembler calculates the address of the location we're going to branch to. The address of this branch point is called the effective address. Before explaining this, we must first set up some conditions. Let's assume that we're using a branch instruction that causes the program to stop if a 0 condition is met. The branch equal to 0 or BEQ instruction happens to be in location 602. The desired halt instruction is at location 612, which is therefore our effective address. You can see that the offset between the PC and the effective address is 3 words forward or +3. Let's assume that the results of the compare were equal to 0, and now the program must execute the BEQ +3 instruction. How does it use this offset of +3 to calculate the effective address? The program takes the offset value of +3, multiplies it by 2, and adds the result of +6 to the current contents of the program counter. Notice that these 2 values added together result in the octal number 612, which represents the effective address of our halt instruction. Thus, the updated PC moves to location 612, which is 3 locations forward from the former PC. Therefore, to find the effective address, the rule is take the offset, multiply it by 2, and add it to the current value in the program counter. The effective address can be calculated by either the programmer or by the PDP-11 assembler. Now, let's study the method for finding the offset when we know the effective address. Suppose there is a large distance between the PC and the desired address. We don't want to spend the rest of the day counting words. Is there some formula we can use to make this task simpler? Yes, there is, and it consists of only two simple steps. First, we calculate the octal difference between the program counter and the effective address. Here you can see that we took the effective address of 632 and subtracted the PC address of 604 to find the octal difference, 26. Because the PC is always incremented by 2, we divide the octal difference of 26 by 2 to come up with the answer of 13. This is the offset value expressed in octal notation. Thus, we can say that the offset value is the effective address minus the program counter divided by 2. Remember this simple formula. It allows you to quickly calculate any offset value when you know the effective address. So far, we haven't talked much about branch instructions themselves. We've spent most of the time dealing with positive and negative offsets. In fact, we've only mentioned two branch instructions, BNE and BEQ. Now we're going to start talking about more instructions. But first, do you remember what conditions the BNE and BEQ instructions test? Did you remember the functions of the BEQ and BNE instructions? BEQ, or branch if equal to 0, tests for a 0 condition. Because a 0 condition is indicated when the Z bit is set, this instruction causes a branch when the Z bit is set. On the other hand, BNE, or branch if not equal to 0, is looking for a non-zero condition and therefore causes a branch when the Z bit is clear. Two more branch instructions test the set and clear states of the C, or carry bit. BCS says branch if the C bit is set, while BCC says branch only if the C bit is clear. Two more branch instructions similarly test the V bit. BVS causes a branch if the V bit is set, and BVC causes a branch if it is clear. Finally, there are two more instructions to test the N bit. If the N bit is set, it indicates a negative condition. Therefore, the instruction testing for the set condition is BMI, branch on minus, or negative. If the N bit is clear, it indicates a positive condition, so the corresponding branch instruction is BPL, branch on plus. In summary, there are 8 separate branch instructions dedicated to testing the states of the 4 condition code bits in the PSW. 4 instructions are used to branch if the corresponding bit is set. The other 4 are used to branch if the corresponding bit is clear. Now that you understand how a branch instruction functions, we're going to show you how to use various branch instructions in a rather large program designed to solve a specific problem. This is the problem. We have a long series of numbers stored randomly within memory. In order to use these values more efficiently, we want to place them in sequential order. Rather than use our normal presentation of first showing you a flow diagram and then the method of implementing the program, let's begin by analyzing the logical steps used to place these numbers in order. If, for example, we wanted to sort 3 numbers into the proper order, then our first step would be to compare the first and second numbers. If the second number is not larger than the first, then we must switch them around to get these 2 numbers in order. Next, we compare the number now in the second position with the third number. Again, we must switch them around if the second number used is not larger. In this case, it means we must switch if the third number is not larger than the second. Finally, we would once more compare the first and second numbers. This is necessary because if we have switched the second and third numbers, we could have destroyed the order of the first 2 numbers. Once again, we would switch them around if the second were not larger than the first. Notice that once the numbers have been placed in the proper ascending order, here 4, 5, 6, any subsequent comparison of 2 numbers would not require any further switching at all. Notice that the condition we want to test is based on the second number. Here, for example, the second number is larger, so we're okay. The numbers are in the proper order. In this case, however, the second number is not larger, so we would have to switch the 2 numbers around to get them into the proper sequence. Let's analyze this comparison process by means of a flow chart. We compare the first and second numbers and then ask the question, is the second number larger? If it is not, then we switch them around to place them in the proper order. If the second number is larger, then we're okay and can keep going. We can use the compare byte instruction to compare the first and second numbers by using the first number as the source operand and the second number as the destination operand. There are three possible results from any compare instruction: a 0 result indicating both numbers are equal, a positive result indicating the source is larger, or a negative result indicating that the destination, our second number, is larger. This last condition is the one we're interested in. Now we can add some instructions to the flow diagram. The compare byte first, second instruction is used to compare the two numbers. We can use a BMI or branch if minus instruction to ask if the second number is larger. If the answer to the BMI instruction is no, indicating that the second number is not larger, then it means we must switch the two numbers. This switching is accomplished by an entire series of steps or instructions, which we will get into a little later. On the other hand, if the answer to the BMI instruction is yes, then we know the numbers are already in order. There is no need to switch them around, and we can branch in order to compare the next two numbers. This small flow diagram we showed you, which was used for comparing the first and second numbers, can be repeated exactly and used to compare the second and third numbers, repeated again for the third and fourth numbers, and so on, until we have completed comparing all of the numbers that we plan to deal with. If we should do this, however, we're going to have two distinct problems. First of all, it would be an extremely lengthy program if we had a long series of numbers. Secondly, and perhaps even more important, when the program halts, it is far from being finished. Any time we switch two numbers, it could affect the order of previous numbers, which might have been correct. Therefore, we would have to run through the entire program many, many times to ensure that all numbers were eventually in order. A better method of doing this would be to use our old friend, the loop. First, we'd compare the two numbers with a compare byte instruction. Then we'd use the BMI instruction to see if we needed to switch them around. If a switch was required, we would perform the switch and then go back to do it all again for the next two numbers. On the other hand, if we did not need to switch them, we'd go directly back to the compare byte instruction and compare the next two numbers. Because we're dealing with two numbers, we need to set up two pointers, a left pointer and a right pointer. Initially, the pointers would point to the first and second numbers. If we then increment both pointers, they would then point to the second and third numbers, which is exactly where we want to be after the first comparison. In addition, by using the compare instruction with auto-increment addressing modes, we can do quite a bit with just one instruction. The instruction is compare B, left pointer, auto-increment, right pointer, auto-increment. The program would first compare the first and second numbers and then increment both pointers so they would move to the second and third numbers. This then is the flow diagram for our basic loop. We use the compare byte instruction with the auto-increment addressing mode to compare the two numbers and then move both pointers. This is followed by a BMI instruction, which tells us whether we should switch the numbers around or not. Regardless of the outcome of the BMI instruction, the program branches back to do it all again for the next two numbers. There's only one problem with this basic loop. How do we exit? The flow you have seen so far will cause the program to continually compare numbers and place them in order. But how does it know when to stop? How does it know when we've stepped through all of the numbers in the table? One solution to this problem is to set a limit. We can pick the point in memory where the table of numbers ends and use this as a limit. Once we reach the limit, we simply start all over again. In order to start over, we would reset the pointers. Now we can step through the whole table of numbers again. You can see that we've added three new blocks to the flow diagram for our basic program loop. The first new block tells us to check the limit after each comparison. Then we ask if the limit has been reached. If it has not been reached, then we keep going. However, if it has been reached, then we first reset the pointers before cycling through the entire program once more. At this point, you might be asking, how do I stop? What you've said so far is just fine. We can compare numbers, switch them if necessary, check the limit, reset the pointers to repeat the program, but how in the world does the program ever stop? How do you know when you've repeated the process enough times to make sure that all of the numbers are in the proper order? Remember what we said earlier about numbers in the proper order? Whenever numbers are in sequence, any subsequent comparisons do not require switching of any two numbers. Perhaps we could use this knowledge to determine when the program has completed its job. Here, we've added a few more blocks to the basic program. The first block tells us to set a code to indicate a switch was made. In other words, whenever the program switches two numbers, we will indicate the switch by setting some type of code. Then, after we've checked our limit and found we've gone through the amount of numbers required, we ask if a code has been set. In other words, have any switches been made? If no code is set, indicating no switches have been made, the numbers must all be in proper order, so we can stop the program. If, however, the code is set, we know we're not finished, so we reset the pointers and the code and branch all the way back to start so we can run through the entire program once more. This, then, is the complete flow diagram for a program that will place random numbers in proper sequential order. Before we start explaining the details of this program, let's take a short break. When you come back, we'll show you how to implement the flow diagram we've just developed.